Let's look at the following example. So, blood test. I would be very surprised if there wasn't a question like this on your final with like disease and how well a tests for that disease. It's a pretty common example. So it is, yeah. Okay, I'll take a look at it. A blood test correctly detects a disease 99% of the time, but also gives a false positive 2% of the cases. Just to make sure everyone's clear, false positive means the person doesn't have the disease, but the test shows as a positive result. That's a false positive. If the disease sure, is present in 1 out of 1,000 people, and the prevalence is 1 out of 1,000, part A is going to be find the probability that a random person tests positive. I will state the formula, but I really encourage you to do a problem like this using a tree. So here's what we're going to say. We're going to say that A is the event of having the disease. I don't think you even really need to write down what A complement is, but A complement does not have the disease. And then B is going to be the event of testing positive, and B complement is going to be testing negative. Okay. So now we want to find the probability of having the disease. Well, sorry, I said the wrong thing. We want to find the probability that a random person tests positive. We know the probability of having the disease. It's 1 out of 1,000. So let's write some stuff down. Typically, when you're drawing this tree, the first branch should be the branch of the probability you know. So do we know the probability of testing positive? Absolutely not. That's what we're actually being asked to find. We do know the probability of testing positive given that someone has the disease or given that they don't have it. But the thing we just know the probability of without any other conditions is whether or not the person has the disease. So at this first branch here, we have the probability of A having the disease. That's 1 out of 1,000. And then in the second branch here, A complement, the probability that's going to be 1 minus 1 out of 1,000, or 999 out of 1,000. That wasn't very close. I feel like I leave myself not enough room for when I draw these trees. I'm gonna start over here and draw this, give myself a little bit more room to work with here. So probability of A, 1 out of 1,000. Probability of A complement, 999 out of 1,000. And then in the second branch, we have the thing that can happen after A has happened. So either you test positive or you test negative. So here, we can either have a positive test given that we have already had the disease. And we know what that probability is. It's been told to us in the problem. So if we read here through a blood test correctly detects the disease 99% of the time, but gives a false positive in 2% of the cases. So that means it's correctly detecting the disease when the disease is present 99% of the time. The probability of a positive test given that someone has the disease is 0.9. And then the other probability in this branch, the probability of not testing positive or testing negative, given that someone has the disease, has to be 0.01. All right, I want everyone to fill out the other branch on their own. So in this other branch, you should have the probability of B given A complement and the probability of B complement given A complement. You already know what one of these is from the words we have written down. All right, so which is it? Is this one 0.02 or is that one 0.02? Well, it says the test gives a false positive in 2% of the cases. So that should be the probability of testing positive given that they don't have the disease. Probably B given A complement. That should be 0.02. And then finally, the other part of that branch should be the remaining 98% or 0.98 probability. Cool, here's our full-fledged tree. Now, if I want to find the answer to this first question, which is what's the probability of the person tests positive, I'm going to find the probability of B. Now, when I'm finding the probability of something, I like to think of it just being all the different ways I can get to that end result. Starting here. So starting here, I can either take this path that goes through A and then gets to B, or this path that goes through A complement and then gets to B. Formulaically, here's what this looks like. Formulaically, it looks like the probability of A times the probability of B given A plus the probability of A complement times the probability of B given A complement. I don't think you need to write that formula down, but that is what we're doing when we're looking at this. Off kilter here. There we go. So in this case, that's going to be the probability of A, which is 1/1000. You could change that to a decimal, right? You could write it as 0.001 if you felt the need to. Times B given A, which is 0.99. Plus probability of A complement, which is 999 out of 1,000. Or if you prefer 0.999. Times the probability of B given A complement, which is 0.02. If you calculate this, it's approximately equal to 0.02097. Actually, it might exactly be equal to that. It might be. Double check. We'll find out. Let's see. 0.99 divided by 1,000 plus 0.02 times 0.999. That's not an approximation, that is exact. So just as a little bit more kind of formula things. So this P of B here, probability of B, what I'm really using there is what's called the law of total probability. If you think about a Venn diagram for a second, where you have like A and B. If I want to find the probability of B, it's really the probability of B intersect A, the overlap, plus the probability of B intersect not A, the stuff that's in B that's not in A. But then that exactly ends up being the formula we've written up here. That's the probability of A times the probability of B given A, plus the probability of A complement times the probability of B given A complement. Again, I don't think you need to really know these formulas to be perfectly frank if you can draw this tree. Okay, but now let's ask the more interesting question, which is what's the probability of having the disease given that you have tested positive? So part B, I think we can put this in here. Probability. Why am I trying to squeeze this in? I have plenty of paper. I don't need to make it fit there. I'm trying not to use all the paper, but so part B, what is the probability of having the disease given a positive test. In other words, what's the probability of A given B? And I'm really just going to look at my tree for this. Going back to the tree for a second. Actually, there's one thing I'm going to do first. Whenever I see a conditional probability, sorry, I feel like my camera's a little bit off here. Let's move this up just a tiny bit. Great. So whenever I'm trying to do a conditional probability, I'm almost always going to start off by saying that that conditional probability, if it's not one of these ones where like I can do the reduced sample space where I'm like, oh, I only need the 4 kings, not the entire set of cards. Here, since I don't really have like a reduced sample space, I'm really going to use the first version of this formula, which is that it's the probability of the intersection divided by the probability of the given thing. I'm always going to jump to that formula because it's really ingrained in my head that that's the formula we use. So after that, then I'm going to think about what each of these things mean. The top part means I want A and B to happen. So I'm going to look at the pathway that gets me A and B. There it is. First A happens and then B happens given that A has happened. And that's the only way that A and B both get to happen. That's going to be probability of A times the probability of B given A. On the bottom, I want the probability of B, which we just calculated, but I'll write it again. It's all the ways you get to B. So it can either be, and look, it's either A and B or not A and B. Those are the only ways we end at B. So it's going to be A times the probability of B given A, and then plus probability of A complement times the probability of B given A complement. And this actually is like the formula for Bayes formula or Bayes rule. This is what we're doing here to get to be starting with this conditional probability of B given A and finding the reverse conditional probability of A given B. I don't think you need to memorize this formula. I'm just writing it out so you can see it a few times. Really, if I was finding this from here, I would jump straight to saying, okay, well, I want that times that. So it's going to be 1 over 1,000 times 0.99 divided by 1 over 1,000 times 0.99 plus 999 over 1,000 times 0.02. That's what I would actually do without writing any of this stuff before it. If we do that, we get about, I think we'll do 0.00099 on top. On the bottom, we calculated that before and it was 0.02097. And that's about 0.047 or 4.7%. So even though this test gives a positive result correctly 99% of the time, getting a positive test doesn't mean you're 99% likely to have this disease. Getting a positive test result means you are less than 5% likely to have this disease. Because it's more about how prevalent the disease is, not about how good the test is. That's more influential as far as how the numbers end up working out here. Okay. Yeah, I don't love that question. We won't do it. Questions about this before we do, I think, one more example, and then we'll move on to something else. To the stuff to the expected value stuff and that kind of jazz. Okay, let's look at a couple more examples. Let's look at that. Say we have an urn or a jar. A jar contains or has 4 red marbles and 6 green. We pick 2 marbles without replacement. What is the probability that the second marble is red? Interesting question. So, if you think about this as a chain of events, the first branch of our tree, the first marble could be what or what? Green or red. Those are the only choices. If there were 3, I could throw in the third color of marbles here. Like if there was white, then there'd be 3 branches, green, white, red, and then we would make the probabilities for each of those branches. So here our branches are the marble is green, the marble is red. Probability of a green marble on the first draw is going to be 6 out of 10. Probability of red marble on the first draw is going to be 4 out of 10. So now we get to come up with these conditional probabilities here. And I really actually only care. So notice I'm only drawing 1 line for this next branch. I don't actually care about my other branch here, although we'll talk about it, even though I don't care about it. So I only really care about the second marble being red. So knowing that the first marble was green, right? Given the first marble was green, what's the probability that the second marble is red, given that the first marble is green? Well, how many red marbles are left? That's how many total marbles are left. 4 red marbles out of 9, that's my probability. I've got a 4/9 chance of drawing a red marble second if the first marble was green. On the other hand, if the first marble was red, now what's my probability that the second marble is red? I should really have been a little more good here, whatever. Probably the second marble is red, given the first marble is red. 3 out of 9. I will point out right over here, if I was finding like the probability of like green, it would be 5 out of 9. Here, the probability of green, red would be 5 out of 9. Or sorry, 6 out of 9. Apologies. So that they still add up to 1 like they should. But I really only care about the straight line, the not dashed lines, the solid lines. That's what I was like, thank you. So the probability that the second marble is red is going to be 6/10 times 4/9 plus 4/10 times 6 times 3/9. Holy smokes, James, come on. Okay, looking good. So I've got, let's see, 6 times 4 is 24. 4 times 3 is 12. Over 10 times 9. I probably could reduce some fractions there. It probably would have been smart to do. I didn't. Oh well. So I end up getting 36 over 90, which reduces to 12 over 30, which reduces to 2 over 5. So 2/5 chance. So it's kind of interesting, I think, that it didn't actually matter what the first marble was. You could have kind of ignored what the first marble was and just say, okay, well, if we ignore the first marble and just pretend like the second, like if we kind of think about the first thing not even having happened yet, and you say, well, out of 10 marbles, what's the likelihood of picking one of the red ones? 4 out of 10 reduces to 2/5. It's kind of weird that it works out that way, but it really is true. In a similar way, just so you can kind of see a similar question, like if I said, what's the probability that the second card picked is a queen in a normal deck of cards? You could do the same kind of thing where you say, well, you have to break it up into either the first card's a queen or the first card isn't a queen, and then kind of make these branching things. Or you say, forget about the first card, pretend like that hasn't even happened yet, and just do the second card first. Maybe the second card first. Well, there's 4 queens out of 52 cards. And it really does work that way. If you do the branching instead, you say, well, you do the queen first, that's a 4 out of 52 chance, times the queen second, that's a 3 out of 51 chance. Or you get a not queen first, it's a 48 out of 52 chance, times a queen second, that's a 4 out of 52 chance. And if you multiply and add these together, it's going to end up equaling 4 out of 52. Kind of crazy. But it's true. Oh, I'm sorry. You guys are like, well, if you say so. Right.
Without replacement, is that like a whole difference?
It is different because then, so it is different, except that you end up getting the same result here. If I said, what's the probability of getting a red marble, a second marble, and then picking red marbles without replacement? Well, probably the first marble is, right, you do the first marble, you get whatever you get, you put it back, and then probably the second marble is red. Well, there's 4 red marbles out of 10 is still 2/5. So in this kind of example, it kind of doesn't matter if you were only talking about what the second marble is. If you haven't also said the first marble has to be something specific. Yeah, let's do one more thing and then we'll move on. A study of smokers found, I'm just gonna give you the bare bones here. Study found that out of 2,000 women, 680 were heavy smokers. 50 had emphysema. And 42 had both emphysema and were heavy smokers. I can't spell emphysema. I mean, I can. So the question we want to answer is, are the events H equal to being a heavy smoker and E equal to having emphysema? Are they independent? Okay, from a purely not mathematical, but logical, knowing what smoking does to your body perspective, do we think these events are independent or not? Probably not, right? If someone smokes, it's probably somehow related or dependent or correlated to having emphysema, or vice versa. If someone has emphysema, it might be related to having smoked. It might not, but chances are that these events are not independent, that smoking raises your risk of having emphysema at some point in life. So how do we test this? Well, the way you can test for independence is you can either test, is the probability of E given H equal to the probability of E? The problem is we don't know any conditional probabilities here. All they've really told us is the following. So maybe that's not going to work. Let me ask everybody, what's the probability of being a heavy smoker? I said H, just H. Well, yeah, so it might not be super clear, but we do mean that 680 is the total number of heavy smokers. And then these 42 that were both are contained in the 680 there. Yeah. Yeah, I started with HS. I was like heavy smoker. Oh no, I was just like, what's probably being a heavy smoker? Yeah, sorry. No fancy notation. That was just terrible writing. So probably being a heavy smoker is, what's the probability again? Right, 680 over 2,000. Similarly, the probability of having emphysema is 50 out of 2,000. And the probability of having both, or the probability of the intersection, is 42 out of 2000. Now, I will point out, you could totally calculate this left-hand side of this equation as that divided by that. Because it is true, the probability of E given H is probability of E intersect H over the probability of H. But in this instance, I would rather just check the thing that felt easier. Instead of asking this, you could ask, is the probability of E intersect H equal to the probability of E times the probability of H? That's an equivalent thing to check. Let's find out. So we already know what this is. This is 42 over 2000, which is actually 0.021. And the question is, does this equal that times that? 680 out of 2000 times 50 out of 2000. Let's find out. The right-hand side is equal to, if you pull out the calculator, 0.0085. So definitely not. These events are not independent of each other. Again, it's not terribly surprising because it's kind of what we expected. All right, that's my finger. All right, let's go ahead, and even though we could talk about conditional probability all day long, I feel like, let's go ahead and talk about, yeah, I feel like we did this already. I'm just thinking of something else. So, was it discrete random variables? Is that what you said? Yeah, okay. I don't imagine, I hope not. I don't think we'll talk about continuous random variables, but so when you hear the word discrete random variables, or specifically when you hear the word discrete, you should think of something that has a finite number of values typically. My usual go-to is like shoe size. Like if we took a poll of all the shoe sizes of people, you'd have some people wearing size 7, 7.5, 8, 8.5, 9, but there's only a finite number of choices. Whereas if I said, how long is everyone's foot? There's an infinite number of possibilities because your foot might be 8 inches, 8.1 inches, 8.15 inches, right? You could get down, your scale of measurement can be really, really fine. And that's an example of a continuous random variable where you can have any value in some interval of values. But we're not talking about that. We're talking about discrete. For discrete random variables, let's look at an example. Let's look at an easy example first. So example A, let's say we had 6 people taking a test. And unfortunately, some of them were not really prepared. And the scores are the following. Scores are 0, 0. They never came to class. 100, 80, 120. I know, right? It'd be terrible if that was your actual scores for a test. But teacher would be like, I did not do a good job teaching because these are all over the place. So let's find the expected value. So expected value, also referred to as the mean, also referred to as the average. These words can have slightly different meanings overall in the stats class, but as far as we're concerned, they all mean the same thing, essentially. So the way we calculate this is that, and so here's notation. Expected value is written as E of X. The mean is typically written as mu. The average is typically written as X bar. These are all measurements of the same thing. If you're taking a stats class at some point, come talk to me. We'll talk about what the differences of these are. But these are all appropriate notations. What is he using in class, or what did he use today? Did he use any of them? He didn't use any of them? That's weird.
Yeah, next little.
And he didn't have a bar over it? Okay. So, well, maybe we're calculating different things. So to find the expected value, I think we all know how to find an average. You add up all the things, you divide by the number of things, which is nice. It's something we're already kind of familiar with. So we're getting 0 plus 0 plus 100 plus 80 plus 100 Plus 20 divided by 1, 2, 3, 4, 5, 6. That's going to be 300 divided by 6, which is 50. Now I want to point out that although you can do it this way, it's not the way we usually think of it. So check this out. I'm going to break this up as 0 over 6 plus 0 over 6 plus 100 over 6 plus 80 over 6 plus 100 over 6 plus 20 over 6. But actually I'm going to write it as 0 times 2 sixths plus 100 times 2 sixths plus 80 times 1 sixth plus 20 times 1 sixth. Or in other words, each observation, each score of 0 multiplied by its probability. Oh, probability one of my students got a 0 was 2 out of 6, because 2 out of 6 of them got a 0. Probability of getting 100 was also 2 out of 6, because 2 out of 6 of them got 100. Probability of getting 80 was 1 out of 6. Probability of getting 20 was 1 out of 6. So you're just multiplying each value by its probability, and you're adding up the results. And it adds up to 50 in this case. So here we're saying the average score or the expected value of the score is 50. Here's some notation. We can write the expected value of x as the sum from I equals 1 to however far you need to go of each x value times the probability of that x value. So in this example, it's the x value of 0 times the probability that x is equal to 0, which is 2 over 6, plus 100 times the probability that x is equal to 100. Sorry, that looks awful, James. Which is also 2, 6, plus 80 times the probability that x equals 80, which is 1, 6, plus 20, the probability that x equals 20. 1, 6. And this is the shorthand notation for that. It's adding up all the things. Stop. Oh, sorry. I'm sorry about that. Someone asked for something. I was like, oh yeah, sure. So the mean or the average or the expected value is a measure of the middle. You're saying, what's the middle of all this data? It's not the only way of measuring the middle, but it's one of the ways we often fall back on. Whereas the variance, as the name might sound like it implies, measures the spread or the variability of the data. We're going to find the variance of the data. Here's how you measure the variance. You're going to take each observation, subtract the expected value, and square it, and then multiply it by the probability. So I'm going to write the formula first this time. So our variance V of x is going to look like each observation minus the expected value or the average squared times the probability of that observation. And as we keep doing this until we run out of observations. Second observation minus the mean squared times the probability of that. And just keep going as long as you need to. Which in the shorthand notation or the summation notation is going to be the sum from I equals 1 to n of x sub I minus the expected value of x squared times the probability of x sub I. There is an alternative formula for this. We can talk about it if we need to. In this particular example, our scores were 0, 0, 100, 80, 120, and then our average is 50. So we make a little table here, our x's and our probability of x's. We had a score of 0 and the probability was 2, 6. Score of 100, the probability was 2, 6. The score of 80, the probability was 1, 6, and score of 20, which is also 1, 6. So calculating this, our variance here is going to equal our score minus the average squared times the probability, plus our next score, which is 100, minus the average squared times its probability, plus our next score minus the average squared times its probability, plus our final score minus the average squared and this probability. Let's see what we get. 100 minus 50 is 50. 50 squared is 2,500 times 2/6. Oh, I missed that one there. Sorry. The first one's the same though. 0 minus 50 is negative 50, and negative 50 squared is 2,500 times 2/6. Here we get 80 minus 50, which is 30 squared, which is 900 times 1/6 or over 6. Same deal here. Negative 30 squared is 900 divided by 6. So let's see. 2,500 times 2 is 5,000 plus 5,000 plus 900 plus 900 is 10,000 plus 1,800 is 11,800, I think. That's about right. 11,800 divided by 6, which is approximately 1,967. The problem with variance is not very, the units aren't nice. So the problem here is like, if you actually had units here, like if you're measuring like, say all these scores were measurements of like inches, for example, just to totally make it weird. I know it's not, I know it's not good. Apologies. But if your measurements were in inches, like let's say the test was to measure accurately the number of inches and you did a really good job or a really bad job. And then your variance, the units would be squared. So your variance would be like, okay, there's 1,967 inches squared worth of variability, which doesn't really make a lot of sense when you're talking about inches and not inches squared. So what we usually do after we find the variance is we take the square root of it. So then the standard deviation, which is the square root of the variance, typically write as sigma equal to the square root of your variance. And it's as easy as calculating that. So really, once you know the variance, you know the standard deviation. In this problem, our standard deviation is approximately, well, it's actually is equal, no, it's approximate, sorry. Square root of 1,967, which is approximately 44.3. So this kind of means on average, each test score that we have is approximately 44.3 points away from the mean of 50. Again, not terribly useful here. We don't have a lot of data. You're saying if you pick one of those tests at random, on average, it's going to be about this far away from 50. Sometimes it's going to be 30 away, sometimes it's going to be 50 away. More often it'll be 50 away. So that means yeah, it seems reasonable-ish, but that's what we're getting. Okay. Question so far. He was using a big X. I wonder. Can you what else do you say in class today? I know that's a big question. Or the highlights. He talked about discrete random variables. Did you give any examples? Okay.
36 blocks.
Sure. Okay, that's not atypical. I would do that too. So I'm guessing he rolled 2 dice, right? And he talked about the average you would get from rolling 2 dice. And maybe the standard deviation as well. Okay, that's fine. It's kind of annoying to do that problem.
But like, what is like the max?
Okay. Let's explore that for a minute. Did we roll 2 dice? Let's say we roll 1 die for a second. Just don't even write this down. So if you rolled 1 die, what are the possibilities? 1 through 6, right? All right, we're rolling a 6. If someone doesn't say it's always a 6-sided die, you could get an 8 or a 20 or a 12 or a 4 or a 10. But 10-sided die are terrible because they're like they're not like a platonic solid. What's that? It's weird. It's like you should look it up. I don't want to draw. I'm not bad at drawing it. It looks kind of like an 8-sided die, except the top has like 5 sides and the bottom has like 5 sides, but they're like the difference between a 10-sided die and the other dice is on the other dice, all of the faces have the same shape and all of the angles between all of the faces are the same. So it's called a platonic solid. There are 5 of them, where all faces and all angles are the same. It's the 4-sided tetrahedron, the 8-sided octahedron, the 12-sided dodecahedron, the 6-sided cube, and the 20-sided icosahedron. So those are the 5 platonic solids. They're pretty cool. There's like, if you ever want to talk about the platonic solids, come see me after class sometime. We'll talk about Euler's formula and all sorts of neat stuff. I shouldn't get too, so anyway, if you roll 1 6-sided die, possibilities are 1 through 6. Each of those possibilities has a 1/6 probability. And so if you roll 1 die, the expected value is going to be each possibility multiplied by 1/6. So 1 times 1/6 plus 2 times 1/6 plus all the way to 6 times 1/6, which ends up being 1 plus 2 plus 3 plus 4 plus 5 plus 6 divided by 6, which is 21 divided by 6, which is 3.5. Which you can't actually roll a 3.5, in case you didn't know. But that's not what the point of expected value is. The expected value means that over time, if you keep performing the experiment, you would expect the average to tend towards 3.5. What if we roll 2 dice? So yeah, then it is kind of annoying to write all the possibilities. There are 36 of them. Again, there's a way to do it being systematic. Let me show you. Let me show you a really fast way of making this table. So I like to think of the first die on here. So this is die 1 over here, die 2 over here. So the first die can be 1, 2, 3, 4, 5, or 6. And then here's what I'm going to do. I'm going to put 1s in the first one all here. So 1, 1, 1, 1, 1, 1. 2, 2, 2, 2, 2, 2. 3, 3, 3, 3, 3, 3. 4, 4, 4, 4, 4, 4. 5, 5, 5, 5, 5, 5. 6, 6, 6, 6, 6, 6. And then in your top column here, or top row, the second die could be a 1, a 2, a 3, a 4, a 5, or a 6. So then we do down 1, 1, 1, 1, 1, 1, 2, 2, 2, 2, 2, 2, 3, 3, 3, 3, 3, 4, 4, 4, 4, 4, 5s, and 6s. I think this is probably one of the fastest ways you can do it. Because I feel like it's easy to write the same number over and over again in columns or rows like this. Is supposed to be like 1, 1, 1, 2, 1, 3, 1, 4, 1, 5. I feel like this is a little faster. So someone could ask you the question like, what's the probability that the total is less than or equal to 4? If I want to roll less than or equal to 4, here's how I can do that. I can roll a 2, or a 3, or a 4. It looks like there's 1, 2, 3, 4, 5, 6 ways of doing that. But really I can write it as the probability that the total is 1, plus the probability that the total is 2, plus the probability that the total is 3, which is going to be exactly, well, I mean, I could write that, but I forgot the probability the total is 4. I shouldn't have written the probability, I mean, it's not like a crime. But the probability the total is equal to 1 is 0. You can't roll a 1 with 2 dice. At least not with 2 regular dice. Probably the total is 2 is 1 out of 36. Probably the total is 3 is 2 out of 36, because you can either roll a 1 and a 2 or a 2 and a 1. Probably the total is 4 is 3 out of 36. This ends up equaling 6 out of 36, which is 1 out of 6. But then the question that I do think is interesting is, what is the expected value? What's the average number you're going to roll if you roll 2 dice? The expected value of X, so people do this all the time, and I'm just as bad as anyone else. I said X, I didn't say what X was. We all know what we're talking about because I've said it, but like we should say that X equals the total number rolled. What I should say is the total number of pips. because that's what the little dots on the die are called, are pips. Total number of pips you get when we can just say the total number. I know you, right? You don't have to say pips. So expected value of X is each possible value multiplied by its probability. So I could definitely roll a 2. And the probability of rolling a total of 2 is 1 out of 36. Plus, I could roll a 3. How many ways can I get a 3? Rolling 2 dice. Get a 1 and a 2, or a 2 and a 1. If you're having trouble distinguishing it or making it that so those are different in your head, pretend like the die are different colored. Pretend like you have a red die and a blue die. You have a red 2 and a blue 1, or a red 1 and a blue 2. Oh, those are different outcomes with the same total result. So there's a 2 out of 36 ways, or 2 out of 36 probability of getting that. And then, but the one thing I want to tell you is, like, you can look at the diagonals here. So here's how you get a 2. Here's how you get a 3, 2 and 1 or 1 and 2. Here's how you get a 4, 3 and 1, 2 and 2 or 1 and 3. Here's how you get a 5. So I've got 4 times 3 out of 36 plus 5 times 4 out of 36 plus 6 times 1, 2, 3, 4, 5 ways of getting a 6 plus 7 times 1, 2, 3, 4, 5, 6, 7 ways of getting a 7. And that's kind of the most. 7 is the most frequent number you can roll on a die. It's got the highest probability of being rolled of any one number. And then the probabilities start decreasing. Number of ways of getting an 8, there's only 5. 6, 2, 5, 3, 4, 4, 3, 5, 2, 6. You get 8 times 5 out of 36. You get 9 times 4 out of 36. You get 10 times 3 out of 36. You get 11 times 2 out of 36. And there's only one way of rolling a 12. And if you add these all up, you end up getting 252 out of 36. Did I actually add those up? No. I knew that the actual answer was going to be 7, because I've done this problem before. The average number you roll, or the expected value when you roll 2 dice, is 7. Now, here's the really interesting part. We didn't have to do all this work to find this answer. We knew that the expected value of rolling 1 die was 3.5. And if you roll 2 dice, you can add 3.5 plus 3.5 and get 7. If you roll 3 dice, the expected value is 10.5. If you roll 4 dice, the expected value is 14. It kind of always works out that way, which is kind of neat. The variance, on the other hand, is not fun to calculate here.